So the next, oh, it's back. So the next big topic that's covered in chapter 1 after unit conversions is talking about significant figures. So a lot of students have a hard time with significant figures, but in fact, significant figures, it's pretty straightforward. Significant figures is talking about measurements that are taken. Not like numbers that are known, but they're the measured numbers in a problem. So the rules for this, all non-zero numbers are considered significant. So in this, that means that all numbers 1 through 9 are considered significant. They're considered a measured value. So if you have 19,826 pennies, then that means that you measured all the way down to that ones place. All 5 of those digits are considered measured. So you sat there 1, 2, 3. So you just sat there and counted and counted and counted. So there's 19,826. So that's all the way down to the ones place is what you measured. So you would say that there's 5 significant figures in that number. So anytime you have a number between 1 and 9 in a measured value, that's considered a measured number and it's a significant digit. So really, it's just the zeros. The zeros are the ones that always cause trouble. Is this a measured number? Is it not a measured number? So in this, I always say that zeros are the troublemakers. Okay, so they're the ones that you've really got to look at. So if you have what are called leading zeros are zeros out front, right? So leaders are always out front. So the leading zeros are zeros out front. They're never significant. Okay, all they're holding is the size. So 0.0025, just 2 significant figures. Just the 2 and the 5 are significant. The zeros out front are not. Lagging zeros, which are zeros at the end, so leading in the front, lagging at the end. Lagging zeros, if there's no decimal place, those are not significant either. So they're really holding, again, the size of the number. So if I had 12,000, so 12,000, these zeros at the end are not considered measured numbers. They're really just holding the size of the number. So with this, if you say you counted 12,000 pennies, just saying 12,000, that indicates that it's somewhere around 12,000. So I'm saying the 1 and 2 are significant, but it might be 12,001, it might be 11,889, but I'm just rounding to 12,000, okay? So I'm just rounding to the 1 and the 2. There's only 2 significant figures in that number. So you see the difference between saying that previous number, where I said I had 19,826 pennies, that's like I measured all the way to the 1. But if I said that I had 20,000 pennies, are they pretty close? Yes. But the bottom number is really a much more exact number. The top number is around 20,000. So I'm somewhere, it might be a little more, a little less, but it's about that amount. And I'm sure you've kind of estimated things like saying, yeah, it's about this. I have about $1,200 in my bank account. Okay, it doesn't mean you have 12,000 cents. It means I have somewhere around there. So it's an estimated number. So when looking at zeros in front or zeros at the end without a decimal place, those are not considered significant. Think of them, those zeros are really just part of an estimate. The only time that zeros are significant if there's zeros in between. So if I say 12,001, 12,001, again, then indicates I measured to the 1. So the zeros in between non-zero numbers, they are always significant. So I measured it, and that just happens to be a 0. So it has the same measurement importance as any other number would have. And lagging zeros with a decimal indicates a much more exact number. So 0.001250, that means that I actually measured all the way to this decimal place. So that ending 0 is significant. So this would be 4. This one would be 5. Zeros in between non-zero numbers and zeros at the end of a number with a decimal place. And it doesn't matter if the zeros are, I'm trying to think how to say this. It doesn't matter if the zeros come at the end, any zeros at the end with a decimal, like I had this one is 0.001250. I could have 1.250. Still, that 0 at the end is considered a significant figure because it means that I measured down to that place. If it was insignificant, I would just leave it off, and I would just say 1.25. But adding that extra 0 means that I actually measured to 3 decimal places, and it's considered a measured value. It's considered significant. Does that make sense? Okay, so we're going to practice a couple of them. Now, just as a note, so when you do converting, when you have to go from grams to milligrams, the numbers that you use in a unit conversion, those are considered exact numbers. You don't count those when thinking about significant figures. They're not going to come into play with rounding, which is the next part. So first, let's just look at some numbers. So this top one, how many significant figures are there? 6, okay? Which one's not? The 0 in the front. Okay, these are the 6 significant figures. The 0 in between, remember, leading zeros are never significant. It doesn't matter how many of them are in front. They're never significant, so there's 6. 12,500, 3. Okay, just these zeros at the end, not significant unless there's a decimal place. So 3. 456.00025. 8, all of them, right? The zeros in between, those are significant. 0.0025896. Five. Leading zeros are never significant, not next. Never significant figures. You always leave those off. They're just holding the size, and you'll see when we convert to scientific notation, those zeros go away because you only keep significant figures in scientific notation. 0.0045100. There is 5. The zeros out front, not significant. What about this one? This is 1,000,000 with a decimal place. So is there 1 or is there 7? There is a decimal place. Those are considered zeros at the end with the decimal. So this would be 7. Zeros at the end, those zeros could be before the decimal place or after a decimal place. Any zeros at the end of a number, if there's a decimal place, they're significant. Lagging zeros with the decimal place. So what about this last one? 7. Okay, all of them are, because I've got a decimal place, so that 0 at the end is significant. So this would also be 7. So we will work on this in lab. We'll also talk about significant figures in calculations, because when you put a number into your calculator, if you take 2 numbers, multiply them, oftentimes you get like the entire screen is one long number, 10 digits or so, but you can't keep all those digits. So this is really where significant figures comes into play, is you're going to need to round your answers. So in rounding, you want to make sure that your answer has the correct number of significant figures based on the parts of the problem. So in multiplication and division, it's all based on significant figures. So if you have 2 numbers, so if you multiply 2 numbers, so 1.89 times 2.5, my answer, and if I just randomly made that up, so in the number 1.89 times 2.5, so I get 4.725. That's my final answer. You see that that's 4 significant figures? So the 4, the 7, the 2, and the 5, 4 significant figures. But my problem, the first one has how many? This is 3, and this one is 2. So my answer has to have 2. So I need to round to the smallest number of significant figures in my problem. Otherwise, it's like I'm making my number more exact than the measurements themselves. So that means when you've got to keep 2 significant figures, you look at your answer, start on the left, just underline the first 2 significant figures you come to, and that means the rest of it gets rounded. So I'm going to keep the 4.7, and that means that the next number gets rounded. And the next number is a 2, so what are the rules in rounding? Do I round up or down? Down. Since that's a 2, anything that's below 5 just gets dropped off. So the next number's a 2, I would just leave it off. So my answer would be 4.7. You keep the decimal place to indicate the size of the number, but since my 2.5 is one of the parts of the problem, I need to round my answer so that it also has the same number of significant figures as the smallest significant figure units in the problem. Addition and subtraction, they don't work that way. Of course. Addition and subtraction, you're going to round to the smallest decimal place that you have in the problem. Okay? So that one, it's all based on decimals. So you just figure out what decimal place do they all have in common? What is the smallest decimal place in common of all of your measured numbers? And that tells you how to round. Remember that anytime the next number is a 4, anything under a 5, it would round down. Anything that's a 5 is going to round up. So like in this, the first one is multiplication. So that means that I have to use significant figures in my number. So 0.120, how many significant figures? There's 3. The 1, the 2, and the 0. 0 at the end with the decimal is significant. 2.782, how many? 4. All non-zero numbers are significant figures. It's just the zeros you always got to double check. So that means my answer needs to have 3. Okay, so first do the math. So don't round first. Make sure you do the math first. So 0.12 times 2.782. And the number that I get is 0.33384. So you see in that's 5 significant figures. I have to round, that's a 0. There's a decimal there. I have to round to 3 significant figures. So what 3 significant figures do you come to? Point what? Is this 0 significant? No, because it's a leading 0. So you don't count that one. It stays, but it doesn't count. So the 3, and the 3. So those are the first 3 significant figures I come to. The next number's an 8, so what's going to happen? That is going to change this to a 4. Anything 5 and up, round up. Anything below 5, round down. So my answer is 0.334. I keep the 0 out front. I keep the decimal place because that shows the size of the number. But I round so that I have 3 significant figures in my answer. 12,500 divided by 3.7. How many significant figures in 12,500? 3. No decimal place, the 1, the 2, and the 5. The zeros at the end, if there's no decimal place, they're not significant. Divided by 3.7, which is 2. The 3 and the 7. So that means my answer has to have 2. 12,500 divided by 3.7. And I get one of those numbers that covers the entire screen. So it is 3,378.378378. And it would be a 378 repeating if I had a lot. Just keep going and going. Can't keep all of those because that would give me 10 significant figures. So I need to round it to 2. So what am I going to keep? I do 3, 3. I've also got to keep the decimal. So make sure that you put that point in because that's the size of the number. So past this, the next number is a 7. What does it do? Round up or down? Rounds up. So that means that this 7 is going to change this to a 4. So it's 3400. Do I put a decimal place at the end? If I put a decimal place, that would give me 4 significant figures. If I leave the decimal place off, then that's 2 significant figures, which is what I need in my number. Okay? I put the decimal place down so I remember to keep the zeros at the end. Because you don't want to take $3,378 and round it to $34, right? You want to make sure that you keep the size of the number. So do make sure you check where your decimal, where the end of the ones place is, so you add zeros if you need to include that size. So addition and subtraction, I told you, are a little bit different. So these ones, not such a big issue what their significant figures are. With these, you're looking at the decimal place. So in the first one, that's a decimal place. 3 decimal places in 456, 2 decimal places in 2.30, 4 decimal places in the 19 number. So what is my number got to get rounded to? To 2 decimals. So I'm going to end up with this because of this one. So that's the smallest decimal place they all have in common. But first, do the math. Don't round till you get done. So 456.025, 2.30, and 19.2544. So I get 477.5794. So find the decimal place they all have in common to 2. Find that decimal place. And so that means that the next number past has got to get rounded. So if the next number is a 9, what's going to happen? So I'm going to round up. So the 7 will become an 8. So 477.58. Same thing with this one because it's addition and subtraction. Do the math, and then I'm going to round to how many decimal places? I'm going to round to 1, 2, 3, or 4 decimal places. 3, because that is the one, the smallest one that they end up having in common. Okay, so just compare them. The smallest one they all have in common is the one you're going to round to. So 25.896 subtract 15.7896, and I get 10.1064. So the third decimal place is the 6. So that means the rest of that has to round. It's a 4, so what happens? It rounds down. So that 4 just comes off. So it would be 10.106 in my answer. 3 decimal places. So they are different. Multiplication and division are different than addition and subtraction. So practice those ones. There's some more rounding rules that you've got. One of the things to make sure that you do is if you have multiple steps, setting it up, kind of like in the unit conversions where we did it in 2 steps straight. If you can do your steps all at the same time, then you get an answer that you can round. Don't round in between. Don't round at each step, because if you do, then you actually may introduce any kind of errors. So your number may end up being slightly smaller or slightly larger than it actually would be. So just remember, round at the end. Scientific notation takes into account significant figures and shows them on a scale of 1 to 9. So this happens a lot in chemistry when you're talking about like the size of one molecule. So one molecule is 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Is about this big. There's a gram on the end there. I ran out of room. That's how small a molecule is. And so if you were trying to do calculations with molecules, you're talking about all these zeros that you have to keep track of. And so putting it in scientific notation helps to indicate the size in a much smaller form. So in doing this, the C is a number between 1 and 9, and it includes all the significant figures in the number. The 10 to the n is the exponent. When you have a number smaller than 1, it is going to be a negative exponent by the number of decimal places that you have to move to make the number between 1 and 9. So in this one, it's a number smaller than 1, so I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I'd have to move 21 decimal places. So this would be 1 times 10 to the minus 21 grams. The number of decimal places you have to move to make your number between 1 and 9. So this is much easier to manipulate. Whereas this 602 with 21 zeros after it, that is a number that we're going to use called Avogadro's number. And that is actually the number of molecules in 1 mole. It represents the formula mass of a substance. That's a huge number, 602 with 21 zeros after it. So using this, keeping track of the blasted zeros, that's really the biggest challenge. And so if we switch it into this exponent scientific notation, you take the decimal place would be here, and you'd have to move by the number of zeros, the number of decimal places, until you make your number between 1 and 9. You keep the significant figures. So when I look at that number, the 6, the 0, and the 2, those are the 3 significant figures. All those other zeros are just holding the fact that that number is really, really big. So you start on this end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So it'd be 6.02 times 10 to the 23rd. So notice here the number is a positive exponent, which indicates a really big number, greater than 1. A negative exponent is showing a really small number, much smaller than 1. So the next challenge in this is to see if you can put it in your calculator. Okay? So if you have a graphing calculator, then, and if you have your calculator, go ahead and get it out. If you don't have a calculator, you guys have at least a calculator. Here. Okay, you have a calculator. You guys can look at this one. So the one way that you're going to put this in a calculator is you have to put in this exponent value. There is, on a calculator, a single button that represents times 10 to the. So on your calculator, do you see this? Look on your calculator. Do you see a button that says capital E, capital E? Okay, that button is times 10 to the. So like in a single button, it'll put that part in. It'll also parentheses your numbers if you do them in any math problem. So for example, take 1.2 put 1.2 EE4. If you have a graphing calculator, you just put it in straight this way. So you put 1.2, then hit, usually it's a second EE, and then put 4. That's saying 1.2 times 10 to the 4th. If you have one of the older calculators like the one I just gave you, okay, put 1.2, hit the EE button. You should see the little number comes up kind of in the upper right corner. It looks smaller than the rest of the numbers. Do you see that? That's the exponent number. Okay, so on the older calculators, that's the little exponent number. For the graphing calculators, you just have an E, then a number. right? So an even a number means times 10 to the, and that's the exponent. The number after the e is the same as the exponent. So this is saying 1.2 times 10 to the fourth. If I was to go, and with the old school calculator, if you hit equals, it should say 12,000. So in this, 1.2, 1, 2, 3, 4, I'd add 3 zeros to the number, so that would be 12,000. So look at somebody else's, did you get it? Yeah, you did it, 1.2, and 4. Okay, so it like goes back and forth that way, and you put that one in, did you see it? Now if you're, yeah, that's exactly right. So the nice thing about the EE button is it does all of that part all at one button. I know you probably are used to times 10 to the little caret. You put like a little caret up and then put the exponent. I don't really understand why your math teachers didn't teach you the EE button, because that like takes all of that out of the way. The other nice thing is if you use the EE button, it actually keeps the number in front and the exponent together. So that you don't have to use the parentheses. So I'm sure you've had to do math and use the parentheses and putting them in. So that's just one that's a little bit faster. Try this other one. So try 2.78 times 10 to the minus fifth. So put that in your calculator. Hit equals 1, 2, 3, 4, 2, 7, 8. And you should come out with a 0.0000278 in your answer. So the old school calculators, the ones that are not the graphing ones, they just automatically put it in like expanded form if they can. But when you put this in, you put 278 EE minus 5. Okay, and the minus is not like the addition subtraction minus. It's the little plus minus button. It's always like in the bottom right side of the keypad. So you see your minus button. So that's the one you would use, not like the addition subtraction button. Make sure that you use the little plus minus button to put that one in. So I did, like I said, that we'll have more sort of practicing with these ones. I did some more back and forth with scientific notation to English in the little review that I did. There's examples that they give on how scientific notation comes into play and how the exponent numbers bigger than 1 by factors of 10 always have positive exponents. Those that are smaller than 1 are always negative exponents. So in this one, if we're going to put this in scientific notation or putting it into standard form, if I have this number, 1205680000, what would it be in scientific notation? How many decimal places to the left do I have to go? Nine. Okay, so if you don't see a decimal place, then you know the decimal place is on the end. Okay, so that means I've got to make my number between 1 and 9. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to move my decimal place 9 times. So 1 point. How many of those numbers do I keep? They have to be significant figures to stay. How many significant figures in the number? There's 6, okay? So I'm going to keep those, okay? I keep the 0 in between because that's a measured value, but I don't keep the zeros at the end. They're just indicating the size. So 1.20568 times 10 to the 9th. So I made it a little bit shorter. $12,500. Oh, stretching. How many significant figures? 3. The 1, the 2, and the 5. Remember, zeros at the end. If there's no decimal place, not significant. But you've got to start from that point. 1, 2, 3, 4. 1.25 times 10 to the 4th. Decimal place goes to the left. That's a positive exponent because my number is bigger than 1. Sometimes it doesn't really change the number so much. So like 456.00025, how many significant figures? How many significant figures in this number? 8. Zeros in between are always significant. They're considered measured. And so all of them are. So all 8 stay. And my decimal place is going to just move how many places? It's just going to go 2. I want to make my number between 1 and 9. So you're just going to move into your decimal places between 1 and 9. So 4.5600025 times 10 to the second. So it didn't really help. Big numbers really, like with lots of zeros, those always are better. What about this one? How many significant figures? 5. So this 2, 5, 9, 8, 9, 6, there's 5 significant figures I have to keep. I have to make my number between 1 and 9, so I'm going to move my decimal place 3 places, and I have to go to the right this time. So 2.5896 times 10 to the negative 3. Negative 3 because it's indicating that's a number smaller than 1 that I had to move. Okay, so you're always going to put your number between 1 and 9. So you find the decimal, and you're just going to move it one direction or the other. If your number is smaller than 1, then you're always going to end up moving your decimal to the right. Okay, if your number is larger than 1, then you're always going to end up moving your decimal place to the left. So notice in this, all of these are numbers between 1 and 9. So you move your decimal place to make your number between 1 and 9. Keep the significant figures. So it's oftentimes the easiest. 1, figure out what are my significant figures. And then 2, how many places do I move the decimal to make the number between 1 and 9? Okay? So like in this one, how many significant figures in 0.00000045100? So there's 5. So these are, right? Zeros at the end. If there's a decimal, those stay. There's 5 significant figures. So I have to start from my decimal place and move the decimal till I get a number between 1 and 9. So from here, 1, 2, 3, 4, 5, 6. So I'm going to move it 6 places. So 4.5100 times 10 to the minus 6. So that's just how many decimal places I had to move it. It's a number smaller than 1. So that's the negative exponent. So in this one, how many significant figures? It's like 1 kabillion. How many significant figures in this? Just 1, right? So it's just this one. All the other zeros, they're just holding the size. So where's my decimal? If I don't see it, where is it? It's on the end. So that's where I'm going to start from. So I've got to count to make my number 1 to 9. So to make this number 1, how many decimal places do I have to go? So you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I had to move it 14 places. 1 times 10 to the 14th. That's a whole lot easier to manage than writing out a 1 with 14 zeros. And that's really when we used exponents the most, is when we're talking about really big or really small numbers, we'll use exponents this semester. Now, if you see an exponent number, remember if you see a positive exponent, you know that that's a number bigger than 1. So if I was going to write this in standard form, like just write it out as a number, which way does my decimal place go in this one? To the right or the left? Here's my decimal. It's going to go to the the other left. It's going to go to the right. You're like my kids. My oldest child she's like left. You're going to go 1, 2, 3, 4, 5, 6. Where all of those are, any past, you've got to add the 0. So 9.5123 becomes 9512300. Same thing with this one, 1.123 times 10 to the 12th. Decimal place is going to go which way? To the right. You're going to have to go 12 decimal places. So 3 of them will be here, 1, 2, 3. But then that means how many zeros do I have to add at the end? You're going to have to add 9 more, right? So the first 3, that counts. So the 1, 1, 2, 3. But then 1, 2, 3, 4, 5, 6, 7, 8, 9. That's times 10 to the 12th. So that 12 is telling you the number of decimal places to move to put it out in expanded form. Now, if you see a negative exponent, that means that's a number smaller than 1. So the decimal place is going to go to the left in this one. So you start here and you're going to go to the left 6 decimal places. So start and put your 9, 5, 2, 1, 2, 3. So we're starting here 1, 2, 3, 4, 5, 6. Here's the decimal. Every one of these little loops I made has to have a 0 in there. A 0 out front just as courtesy to hold the decimal in between something. So practice those ones. Also practice putting them in your calculator. So if you left your calculator at home, do make sure you go back and kind of double check that you know how to do these. Let me know if you have problems with them. So in percents and density is covered in chapter 1 as well. So percent is represented by that symbol, the percent. And most everybody understands percent because they think about it in terms of a grade. So if you got an 80%, then that means that you got 80 out of 100 questions right. So this is what you got compared to the total possible points. I used to teach with somebody that used to write exams based on how much information he covered. So he would sit down and write exams. If he had covered a lot of information, he would have a lot of questions, and every question was worth 5 points. So sometimes he'd end up writing a 5-page test, and that test would be worth, say, 750 points. That's the total possible. So you would get a grade back, and you might have gotten 620 out of 750. So then students are like, well, what kind of grade is that? So looking at that number, this is the possible compared to the total. To keep it on a scale of 0 to 100, that is why you use percent. So this is your possible, or this is the number that you got right, divided by the total possible points you could have gotten. If you divide this, it's going to give you a decimal place. So that's why you multiply it times 100. So that puts it on a 0 to 100 scale. So he would sometimes have these really big exams and cover lots of information. And then sometimes he wouldn't have all that much that he covered, so it was a pretty short span. So sometimes you'd only have, say, a 420-point test. And so say that you got 310 questions out of 420. So notice when you look at those, just randomly looking at them, you sometimes like, I'm not really sure like what that grade is. So the easiest way to do it is to take your grade divided by the total possible points, multiply it times 100, and that gives you a percent. So what's that first one? So what'd you get for the first one? So if you took 620 divided by 750, $620 divided by 750 times 100, and I got 82.666666667. Okay? So it's like an 82.666667. Can't keep all those numbers, so here's your rounding. So when rounding, I don't count the 100. That's not a measured number. 620 and 750, those are measured numbers. How many significant figures? 620 has 2. 750 has 2. Okay, so since I have those 2, my answer needs to be rounded to 2 significant figures. So what would I round that to? That would be 83. I keep the 8 and the 2. The next number is a 6, and it rounds the 2 up. So I would say that I got an 83% on that test. So what if I got a 310 out of 420? Did I do better or worse? I did worse. Okay, when you just look at it, you may not have known just from looking at it and comparing those numbers. Putting in a percent gives you this scale of 0 to 100. So I got in this one, I got 73.8095281%. Can't keep all of those. How many significant figures do I round to? 2. 310, the 3 and the 1 are significant. 420, the 4 and the 2. So I'm going to keep these, and that number becomes a what? A 74. So that 8 is going to round my 73 to a 74%. So whatever the measured value divided by the total possible can allow you to put something in a percent form. So look at this bottom question. So 2 infants are in the perinatal ICU. Okay, so they're newborns, preemies. One infant's weight increases from 126 ounces to 147 ounces. The other infant's weight increased from 86 to 103. So what you want to know is which infant had the greatest percent weight increase. So how do I figure out the weight increase? What do I have to do first? What was the increase for infant 1? What was it? It was 21 ounces. You just subtract. So I subtract the original weight from the final weight. They gained weight. So 147 minus 126 tells me that there was, baby 1 gained 21 ounces. So you see the difference. So it's asking the difference of those two numbers. Baby number 2, what was it? So 103 minus 86 is 17 ounces. So one gained 21, one gained 17, but we want to know what is their percent. So they gained 21. What was their starting weight? So you're comparing how much weight they gained compared to what they started at. So how would I figure out the percent for infant 1? Be 21 ounces divided by what? 126. Multiply your answer times 100. Got 16.766667%. What would I need to round that to? 21 divided by 126. So my answer should have how many significant figures? 21 has 2. 126 has 3. So remember, I always have to round to the smallest number of significant figures in the problem. So this one should be 17%, 2 significant figures because of that 21. What about the second one? I'm going to take 17 ounces and divide it by what? 86. Multiply that answer times 100. Gives me 19.7674418%. Sorry, I ran off the board. What should my answer get rounded to? So I have 2 significant figures in 17, 2 significant figures in 86. So that means my answer has to have 2 significant figures. So this 7 will do what? Change it to a 20. Now if I just write 20%, how many significant figures in 20%? There's only 1, so how do I make that 0 significant? What can I add? Put the decimal. So you see that that 20 is now 2 significant figures in the number? Okay? So it may have looked like baby 2 gained less weight, but baby 2 was smaller to begin with. So baby 2 actually had a greater percent weight gain. And so in comparison, using percent helps you to compare numbers that may not have the same scale, but by putting them in a percentage, now suddenly you're putting it all on a scale of 0 to 100. So it can make 2 numbers much more comparable than just looking at them individually. So you're going to work with accuracy and precision, especially in lab. We're going to look at accuracy. We will try to get the right answer. Don't always get the right answer. But accuracy, that's exactly what it is. Accuracy is whether or not your answer is right. I always think of accuracy as sort of like each time. It's an individual or a one shot. If you're accurate, you hit the bullseye. If you're accurate, you get the right measurements. So if you're accurate, you come out with the number that's supposed to be close to the standard or the reference value. Precision, though, is really based on repetitive answers. So you hit the exact same spot if you were throwing darts, okay? If you were shooting arrows. So you're hitting the exact same spot every time. Not always that you're hitting the correct spot, but you're hitting the same spot. In order to hit the same spot, you have to have the same technique. You have to go through the same steps. You have to be careful in measurements. If you're talking about shooting an arrow, you align yourself exactly the same, you point at exactly the same spot, you pull the bow back at exactly the same pressure. That's going to allow you to do something over and over and over again. So the people that bowl, okay? So bowlers will throw like strike after strike after strike because they do it exactly the same. And they just practice that, they practice that, they practice that so that they can do that. And they're like, the lane's exactly the same, none of that changes. And all they have to do is just be off by just a hair in their hand force, and that can cause the ball not to hit the strike. So it seems like it would be very easy. But doing things over and over and over, that's precision. Okay? The more precise you are, the more you will be able to do things over and over. You can be both. You can be accurate, you can be precise. You can be accurate and not precise. You can be precise and not accurate, and you can be neither, okay? So if you were accurate and precise, and we were looking at some type of target, if you're accurate and precise, where are all, and you throw something 5 times at this, throwing the hatchet, where are you gonna hit it? Right in the middle. If you're accurate and precise, 1, 2, 3, 4, 5. Lots of accuracy, lots of precision. Right in the middle every single time. But what if I am accurate but not precise, and I throw it 5 times? What am I going to do? You may have 1 or 2, but then the other ones are all off. That's still considered accurate. That's pretty good, right? You hit the bullseye twice. But the other ones were like wild. With a hatchet, that's never a good thing. Okay? But at least it didn't hit anybody. So in that, this would be accurate, but not precise. And this is oftentimes because of technique. Because maybe it slipped, okay? You didn't line up the same every single time. And so in here, your method was a little off, and that's why. It's the hardest part about things like bowling, is actually trying to line up and throw it exactly the same way every single time. What if you're precise and not accurate? Where would it be? If you're precise, but not accurate, what would you see? 5 spots where? Okay. Scattered or all in the same area? So 1, 2, 3, 4, 5. That's precision. I threw it. I just missed every single time. But I'm throwing it with the same care. I'm throwing it the same, and it's landing in the same spot. Not necessarily in the bullseye, but this is precision without accuracy. This can sometimes happen if your equipment's off. Okay, so like when you think of a bow and arrow, if you're aiming and you're off every single time, you need to recalibrate the bow. Okay, you end up having to adjust either where the sight is, or you have to adjust where you're actually aiming at to try and put it in. But your measurements are really good because you're hitting the same spot every time. And then what if I have neither? Where would I see? What if I'm not accurate or precise? Yeah, either that, you'd be like this. Okay, nowhere near the center and nowhere together. So having it totally scattered. Having precision in lab is all on you. Trying to make sure that you take careful measurements, taking in significant figures when you're doing calculation, that you're doing proper rounding. All of those things are going to increase or improve your precision. Sometimes accuracy is like luck. So sometimes accuracy is because your equipment is perfect. Your equipment has been calibrated recently. So your equipment there hasn't been salt dumped all over your balance like in the previous lab, and now it's all up underneath the balance and it's all crusty. Okay, those things kind of happen, but you can still be precise. Precision is really based on like your efforts in trying to keep measurements the same. So we've talked about mass, we've talked about volume. So remember that mass is the amount of substance something has. We always think of weight. Weight is in reference to gravity. So mass is really just the amount of a substance that something has. Volume is the amount of space it takes up. So remember we said matter has those two characteristics. Matter has mass and it takes up space. Mass depends on how much you have. So you could have like a lump of carbon, or you could have a bottle of carbon, or you could have like a shovel of carbon. So that changes or varies depending on how much. Same thing with volume. So volume is variable. Volume, you can have like a cup of water, or you can have a teaspoon of water. So those volume amounts depend on the substance. One note that you will see is a measurement of milliliters when you're talking about a liquid. So milliliters is equivalent to what they call a cubic centimeter. So a cubic centimeter is a volume, a cube, like a block, that is 1 centimeter tall, 1 centimeter wide, and 1 centimeter deep. Okay, so it is like an equal side centimeter, and that is 1 milliliter in volume. So if you see a cc, or if you hear cubic centimeter, or if you see 1 milliliter, those are the exact same unit volume. This is commonly used with syringes. So you get a 3 cc syringe, that's a 3 mil syringe. So those ones, you can flip those numbers. You don't have to do a unit conversion or anything. They're saying the same number or the same volume. But one thing that's also consistent in substances, whether you're talking about an element or a compound, is density. So density is how heavy something is compared to how much volume it takes up. So it's mass divided by volume. And it doesn't matter how much mass, pure substances will take up a certain volume. So compared to the mass, compared to its volume, is actually a standard value. So example, water. So water became sort of one of the standards that almost all of this metric stuff was built around. 1 gram of water takes up 1 cubic centimeter. It has the volume of 1 milliliter. So it's a very 3 significant figures in the number. So its value is determined to 2 decimal places, that there is 1 gram of water takes up 1 milliliter of volume. So if you have a sample of water and you add a substance that doesn't dissolve, So it's got to be a solid and it can't dissolve in the water. If it doesn't dissolve and it floats, then you know that it's less dense than water. So it has less mass compared to its volume. And so they give you the example of a piece of wood. So it's less dense, so if you set it on top, it's going to float. If you take a penny, a metal, you put it in water, it's going to drop to the bottom. So since it doesn't dissolve and it goes to the bottom, it has to have greater mass compared to volume, so it is more dense. So this is sort of an easy way to distinguish more and less dense substances. As long as they don't dissolve in water, you can use water for that comparison. But if you get a mass measurement and a volume measurement of any sample, you can determine its density. And sometimes finding a substance, if you can determine its density, you can figure out exactly what that substance is, as long as it's a pure substance. So this one, if you have a 1.00 liter volume of sugar, and it has a density of 1.29 grams per milliliter, what is the mass of the sugar in the sample? So when you read anything that's in a sentence form like that sometimes throws people. They see it as a word problem and they're like, this is too hard. Things that you want to do is, one, what do you know? So what do I know in this? You can just underline them as you go. So look at the number values. So a 1.00 liter volume. So I know volume. I also know density. What do I want to find? The mass. Okay? So find the pieces that you know, figure out what the question is wants you to find. So I want to know mass is what? So the formula that I need to use is density is mass over volume. But I want to know mass. So in order to find mass, what do I have to do to this formula? Can I use it as it is? No. I've got to rearrange the formula. I need to put mass all by itself. So here's mass. So that means I've got to move volume, right? Because to be able to solve for mass, you put it all by yourself. So volume is in the bottom. How do I move volume to the other side? Multiply both sides by volume. Times volume times volume. What's that going to do to the right side? Yeah, volume will cancel. So since volume's in the denominator, when I move it to the other side, it ends up in the denominator. So if I take volume times density, that'll tell me mass. So can I multiply volume times density? Second thing to do, so one, rearrange formula, or double check. Maybe you can use the formula as it is. If not, you've got to rearrange the formula. Second thing that I need to do is check the units. So can I multiply volume 1 liter times density 1.29 grams per mil? No, because I have liters and milliliters. So I can't multiply those directly. I've got to put the liters or milliliters in the same units. They've got to match so that they'll cancel. I always find it's easier to change the one that's like single, so I'm going to change volume. Because that'll put it in milliliters, it'll put it in the same units that I have with density. So 1.00 liters times, what unit goes on the bottom? Liters on the bottom, milliliters on top. Unit I'm given always goes in the bottom in the first one. Unit I want to go to, since I have liters, it's a base unit, it's just a single step. Milli means 1,000. Anytime you have milli, you're going to put 1,000 in front of it. It takes 1,000 milli to make a base unit. So liters and liters will cancel. So 1.00 times 1,000 is 1,000 milliliters. Now I can multiply them, okay? Because now my volume in my volume and density, same unit. So I said volume times density, so 1,000 milliliters times the density is 1.29 grams per mil. That would be like grams per 1 mil. So see how milliliters and milliliters will cancel? 1.29 times 1,000. It's 1,290 grams. Now the last step. So in the last step, significant figures. How many significant figures in my volume? And I always go back and look at the original problem to make sure my significant figures are right. Okay? So in this problem, 1.00 is how many significant figures? How many here? There's 3. So I have 3 significant figures in this. That's my measured volume. Okay? So that's my measured volume. Density is actually something you look up in a book. So that's considered a standard or a reference. So I actually don't use that in significant figures. So this is a reference number. I didn't measure it myself. This is the thing that I measured. So you always look at the measured value when figuring out significant figures. So what do I have to do to my answer? 1,290. Do I round it? It's fine, right? So the 1, the 2, the 9, those are 3 significant figures. I don't need to add a decimal place to the end. I just leave it. That 0 is there indicating the size. This has 3 significant figures, just like my problem. All I did was multiplication. Okay, so just make sure you get all the way to the end before you think about any kind of rounding. So temperature. Temperature is another measurement, and it's really just a measurement of the amount of hotness or coldness that something has. I think of it as being vibrational activity. Remember that we said that gases have the highest energy compared to solids and liquids? That they're moving all the time. So you think of these molecules as doing this. So if they're vibrating, they're releasing this energy, and that's felt as heat energy. So if you have your hands around something that's warm, heat gets transferred from the warm thing to your hands. If you're holding on to a soda, then heat gets transferred from your hands into the soda. So that transfer is because of that vibrational heat energy that the substance has. So in the United States, we use Fahrenheit. Everywhere else in the world, Celsius. And the reason they started with Fahrenheit is an environmental scale. Which means they actually recorded the coldest temperature and they said that's 0. So the coldest day became 0 degrees Fahrenheit. The hottest day, and this is primarily in Eastern Europe, the hottest day became 100. So that's where their scale of 0 to 100 came in. Kind of seemed like random day, like random measurements, because like if you were living on the Mediterranean, that wouldn't actually match. Okay, it's a good thing they weren't like living in the tropics, because the days are like 60 degrees to 90 degrees. We would have had a really small scale to go through, but this was more European values, and so coldest they said was 0, hottest they said was 100. So how's Celsius different? What is 0 degrees Celsius? What's the 0 with Celsius? What's 100 degrees Celsius? It's really hot, 212 degrees Fahrenheit. That is the temperature at which water boils. So this is the boiling point of water. 0 degrees is the freezing point of water. So it's the point where water freezes or water boils. So they went more with water as the standard reference compared to the environmental scale. the ones that I want you to be familiar with are these, okay? I don't expect you to have to convert Fahrenheit to Celsius or Celsius to Fahrenheit, but you should know the comparisons between the two. So the boiling point of water is 212 in Fahrenheit, 100 degrees Celsius. The freezing point of water is 32. It was actually colder than that this morning. It's like 26 when I left the house. 32 degrees Fahrenheit, 0 degrees Celsius. Okay, so that's the 0, 100, and that's the Fahrenheit comparison. Body temperature. So this is one that you will use very common. 98.6, that is normal body temperature. 37 degrees is normal body temperature in Celsius. So those are the two. And then the last one is room temperature. So room temperature, 75 degrees, they say it's about 25 degrees Celsius. It's pretty close. It's really like 75 degrees is really closer to like 23 degrees Celsius, but they use them about interchangeably when talking about regular room temperature. So those are the ones to kind of compare, or the ones to be familiar with. There is like a conversion for that. But like I said, I don't expect you to like do the math conversion between Celsius and Fahrenheit. But if you did, this is the one that you would use if you have Fahrenheit and you want to go to Celsius. So you can plug F in, the Fahrenheit number, subtract 32, then divide it by 118. Remember, do anything in parentheses first when you do math. For the other one, if you have a Celsius number and you want to figure out Fahrenheit, you take the Celsius number times 1.8, do that first, then add 32 to your answer. I'm not going to ask you to do that on a test, but if you needed to use those would be the ones that you would want to use. Those are sort of the easiest ones. They don't have the same scale. We will talk about Kelvin later on in the semester. Kelvin is used primarily when talking about scientific measurements using gases. Kelvin is actually considered the coldest possible temperature that you can achieve is 0 degrees Kelvin. It's the temperature where molecules just stop vibrating. So that's like they would have no vibrational activity, they would have no temperature. They made that 0 Kelvin. And we'll use that with gas laws. So I'll explain it to you when we get there. So we talked about potential energy, kinetic energy, and how energy changes forms. So you can go from chemical energy to mechanical energy, going from food to powering muscles. Okay, so you can convert from one form to another, having nuclear energy in order to convert it to electrical energy, like a nuclear power plant. So we talked about examples of that. We will talk a little more about food calories, calories in nutrition, the amount of energy that is gained from the various nutrients of carbohydrates, proteins, and lipids in this semester. When thinking about temperature, I said it's the vibrational activity. Well, heat is this flow of energy from something that's warmer to something that's cooler. So, like I said, you can feel the heat from your coffee cup because the coffee is warmer than your hands are. Well, substances have known abilities to absorb energy and change temperature. So they call this specific heat. Specific heat is defined as being the amount of energy that a substance can absorb before it changes temperature. Water has a really high specific heat. So water changes temperature very slowly compared to metals. So look down here, see aluminum is 0.21, water is 1. So water can absorb 5 times more energy given the same mass before it's going to change temperature. So if you've ever gotten in a swimming pool like early, like close to Memorial Day, so they open the swimming pool and so you go and you're like, it's like freezing cold. Even though maybe it's been 80 degrees for the last 5 days, that water is still cold and it takes weeks for it to warm and warm and warm. But then in September, you have like cool nights and you put your foot in the water and it's like nice and warm. The water's like 70 degrees, even though it's like 50 degrees outside, because water heats up and cools down very slow. It has to absorb or release a lot of energy before it changes temperature. That's really good for us because look at our specific heat. Because we're roughly 2/3 water, the human body has an overall specific heat of about 0.8. So it doesn't heat up and cool down near as fast as metals do. It doesn't heat up and cool down. I thought maybe they had ethanol in here. Ethanol is a whole lot lower. Its specific heat is about 0.5. And so ethanol will change temperature much more rapidly, but we're not going to. So having water as our primary fluid means that we maintain a very consistent body temperature. So that 98.6, it actually requires a lot to raise the temperature or to cause it to drop. It stays relatively consistent even though you go outside and it's 26 degrees outside. Or you go outside and the heat index is 110 in the summer and you're like, when you're out there, just remember that. That's not that far away. Another 4 months. We'll be talking about that already. But your body temperature stays the same. So your body temperature always is responding to try and make sure that temperature stays consistent. So there are changes in the body that occur, but specific heat really helps to keep that body from changing a whole lot. Great example of water's specific heat ability. Think about in the tropics. So if you've ever been to any place close to the equator, okay? So like we've been to Cancun twice. So Cancun at night, it's about 70 degrees, okay? It's like 98% humidity. My hair's like out to here. And you're like, you go outside and you're just walking, you're like, oh, I'm sweating already. It's like, it's dark out, but it is 70, 75 degrees at night. And then what does it get to during the day? It gets up close to 90 Fahrenheit, okay? Just environmental, you don't get a big, huge shift. And that's because of the amount of moisture. So it doesn't cool down very fast, it doesn't heat up. But what about the desert? Has anybody ever been to the desert? Okay, so what's it like at night? Cold. Like what kind of cold? Like freezing cold. Like it can drop to like 40s at night. And then during the day, like Arizona routinely will have not heat index, just regular temperatures of 110. Why? I was in Arizona in February a couple years ago. It was like 85 degrees in like the first week in February. I was like, it's so hot and dry. Geez, it's dry. There's like no moisture. So what happens? Temperature shifts dramatically, okay? Because of the amount of water in the tropics, the temperature range stays close to the same. It just stays hot and muggy all the time, at night, during the day. But in the desert, you'll have this dramatic drop. As soon as the sun goes down, temperatures start to plummet. And as soon as the sun comes up, everything warms up, and then it gets really warm during the day. And that's all because of water. High water content, low water content. So that water content really helps to maintain this balance. All right, I will quit there. Yeah, we're good. I will quit there, not there. And if I could figure out how to make a stop.